So our first paper motivates our search and explains what we're doing and how it's different from maybe traditional communication SETI. Let me just start with something I've been saying in a lot of places and trying to emphasize. What is SETI? The search for extraterrestrial intelligence. It's a lot of things. It's researchers, it's places, it's things, but most of all, I think of it as a field of study. It's related, of course, to astronomy and radio engineering and astrobiology, but it's a field of study, an interdisciplinary one, and it has many components that complement each other. The most famous component is, of course, Jodie Foster at the VLA from the film Contact. This is what most of us have in mind when we think about SETI because it's perhaps the most famous component of the search. The philosophy behind this goes back to a classic paper in 1960 by Cocconi and Morrison, when they realized or published a paper arguing that it should be possible to communicate across interstellar distances with modern radio technology. Radio astronomy was just coming of age, and in this paper they did the calculation and showed, perhaps surprisingly, that sending a signal with the technology we have today or had in the 60s to the nearest star, that signal would be detectable with current technology if we had a comparable receiver at the nearby star. And Frank Drake was also working along these lines at the same time. So that line of communication SETI today has many forms, perhaps most famously the Allen Telescope Array, which is operated by the SETI Institute to pursue that vision and search for signals, radio signals from extraterrestrial civilizations across the galaxy and even beyond. The search, though, is largely funded privately. This whole field, SETI, gets very little, if anything, in the way of federal funding through the traditional ways that we fund science research. And so it really relies on private philanthropy and people that are excited about it, as with the Allen Telescope Array, for instance. But most recently, there was the $100 million commitment by Yuri Milner to launch the Breakthrough Listen initiative and the Breakthrough Message initiative to really push communication SETI forward and make it a much bigger project than it currently was. So this is now ongoing. The Berkeley SETI Research Institute or Center is doing a lot of work to make this happen. One of the places that this is being done is the Green Bank Telescope, operated by the National Radio Astronomy Observatory in West Virginia. It's the largest steerable dish in the world and a great instrument for detecting extremely weak radio signatures from space. The Breakthrough Listen project has purchased a large fraction of the time available on the telescope and has installed all sorts of cool hardware on the back end to improve its ability to detect signals from other stars. So that's what we think of when we think of SETI a lot. I'm not a radio engineer, I'm not a radio astronomer, but I was interested in helping with the SETI project. And so I don't build things like this, and I was wondering what else can I do to contribute to the effort. But it turns out there's another strand of SETI that goes back also to 1960 to a paper by Freeman Dyson. He pointed out that if you have a civilization that uses energy, and if you have an old civilization, and we think alien civilizations are very likely to be significantly older than us because we just got started and the galaxy is billions of years old, they might use a lot of power. They might use significantly more power than we do, many orders of magnitude more. They might use a significant fraction of the available starlight to power whatever it is alien civilizations do. And if they use that much energy, we think about using energy, but of course you never use up energy. You have to conserve energy. Once it's done the useful work that you want it to do in your computer or whatever it is, you then have to get rid of it in a higher entropy state, and that's usually called waste heat. So your computer does the work, and then your computer heats up and it radiates that energy away that it got out of the wall. So energy is never used up. It's just converted to a higher entropy, a lower temperature than it was when you got it. So you have this very hot star that's producing a lot of energy. You collect it, you use it, and then you radiate it away at lower temperatures, longer wavelengths. And it will usually come out in mid-infrared radiation for most reasonable temperatures. And so he said that this is a very general approach. It doesn't matter whether they're intentionally signaling us. It doesn't matter what they're doing. If they're using huge amounts of energy, that energy has to go somewhere when they're done with it. That's bedrock thermodynamics. And so he suggested that we look for stars that have an excess of infrared radiation coming off of them that might be indicative, essentially, of the tailpipe of the civilization. So where do you look for this? How big could these civilizations be? Is that really practical? In 1964, Nikolai Kardashev published a paper where he speculated how much energy could a civilization use. He wanted to know, they have a lot of energy available to them, presumably. This sets a limit on how powerful their radio transmissions might be that we might look for. So he defined a type 1 civilization that could harness an entire planet's energy supply, all of the starlight that falls onto the planet. A type 2 civilization can harvest the entire star's output, so you could imagine surrounding the star with a swarm of solar panels. And a type 3 civilization not only does that, but also has interstellar travel, and does so to all of the stars across an entire galaxy. And so once you've harvested most of the stellar energy in an entire galaxy, that would be a type 3 civilization. And the timescales here are such that the time it would take a civilization to do such a thing, by most measures, is much smaller than the amount of time galaxies have been around. And so there's no physical reason that there couldn't be such civilizations throughout the universe, spanning and collecting all the energy from whole stars, collecting all the energy from whole galaxies. So in the 1980s, a satellite called IRAS was launched to map the entire sky at infrared wavelengths. And one of the science outputs of that would be a search for stars that have infrared excess, and perhaps looking for these type 2 civilizations. This was complicated by the actual map, which ended up looking like this, revealing that the galaxy is filled with glowing dust at these infrared wavelengths. This is the infrared cirrus. And that creates a background against which you're trying to see stars that might be giving off infrared light. That made the satellite much less sensitive to waste heat than people had hoped, and so it wasn't actually a very efficient way to go looking for so-called Dyson spheres or stars giving off a lot of infrared light. We also learned that there are a lot of other kinds of stars that naturally give off infrared radiation, further complicating this idea. Nonetheless, one intrepid astronomer in particular, Richard Kerrigan, you'll see this was published in 2009 based on that 1983 satellite, so this was really a hobby on the back burner for him for a long time. He finally went through the entire catalog and checked out every bright star and studied it carefully to try and figure out if we had any good candidates in the data set, and he found lots of sort of candidates, but upon further inspection, he discovered that they're all things like carbon stars, active galactic, asymptotic giant branch stars, or H2 regions, which are all very astrophysically interesting. And so there's a lot of great science coming out of it, but there was nothing that just said this is aliens around that star. So that was, that I think remains one of the only firm upper limits on how many of these civilizations exist in the galaxy. So we can go a step up to galaxy-spanning civilizations, type 3 civilizations. That was the only search I'm aware of to date before ours was also at Fermilab, a guy named James Annis. And he looked for galaxies that were too dim. The idea is that if you surround the star with solar panels, less light will get out than should. So he wondered, are there any galaxies out there that just the surface brightness is too low? You know the mass dynamically from how the stars move around the galaxy. Are there any that just don't have enough light because perhaps it's being blocked? So he wasn't looking for mid-infrared light coming out. He was looking for a lack of optical light from stars coming out. Anyway, he did the search in galaxies in a cluster and didn't find any strong candidates showing that there aren't any extreme cases of a type 3 civilization in that galaxy cluster. So that's where we came in, and I got thinking about this when we saw a talk at Penn State by an old friend of mine, Mike Cushing, who showed that the WISE satellite, which had recently published a lot of its data, had discovered a brown dwarf with an effective temperature around 300 Kelvin. So that means that this is a failed star. It's about the size of Jupiter, but much more massive, not as massive as a star, so it's not fusing hydrogen. And so it's only warm because it got put together and it was hot, and it's been cooling off ever since then. And it was basically a room temperature object that WISE had discovered in space. And that's also about the temperature that humanity, our civilization, gives its waste energy off at, which means that the WISE satellite was sensitive to exactly the wavelengths that you might expect to find waste heat at. And it also searched the entire sky. And it did it in a way that was much more sensitive than IRAS had. So this was a new opportunity to try and improve on the IRAS upper limits. So our strategy was to use that, that data to go and see what we could find. And we were able to do this through a grant that ultimately came from the John Templeton Foundation. So again, this is private philanthropy funding SETI. So the one problem is if you just look for points of light that have lots of infrared radiation, you don't know necessarily if it's a star right away. WISE detected 100 million sources. And so going through all of those is quite a challenge. It'll be easier in the future once we have more data to figure out what they all are. But for now, that was a bit daunting. So we restricted ourselves to looking for type 3 civilizations, the way James Annis had, that is only looking at galaxies where you could actually see the whole galaxy in the image, not just a distant galaxy that's a point of light, because that could be almost anything. So here's an image of a nice spiral like our own. This is the great galaxy in Andromeda. And you see the dust lanes in the spiral arms. That dust is actually glowing very brightly at mid-infrared wavelengths. And then the soft glow everywhere that you see is just from 100 billion stars all giving off their light. So if we put on our infrared goggles and look at this, so we'll switch over to a Spitzer image of the same galaxy, you see all of that dust that used to be dark is now bright and glowing in the infrared. So this tells us a couple things. It means just seeing infrared light from a galaxy isn't surprising. Dust does that. But it also tells us that dust tends to be clumpy. And if you look between the red lanes, you can see regions where there's hardly any dust coming out, glowing at all. If instead we had just seen a smooth distribution of infrared light, that would mean that the infrared light was coming from the smooth distribution of stars, not the clumpy distribution of dust, and that would have been very interesting. So by being able to resolve these galaxies, we can distinguish cases that might be filled with alien civilizations versus ones that are bright because of dust. I'm going to show one of these later, so I just want to explain what it looks like. This is a spectral energy distribution of a galaxy. So the black line and the red line goes on top of it towards the left, represents how much energy an old elliptical galaxy gives off, one that essentially has no dust in it at all. On the left, you have optical light. On the far right, you have far infrared radiation. And then right in the middle, those purple bands that go up and down, those are the wavelengths that the WISE satellite was sensitive to. So the right-hand ones at around 10 and 20 microns, there's very little emission that you would expect to see from a galaxy with no dust at all. But if just 1% of the starlight were being intercepted from that galaxy and being used for some purpose and re-radiated at around 300 Kelvin, it's not too sensitive to what temperature you pick, there would be a significant excess of infrared light. And so WISE would see that it was a little too bright. And then if you have a galaxy that's filled with dust and star formation and is inherently very bright, you'll get something like the green curve here. This is a famous starburst galaxy called ARP 220. It's very bright at those infrared wavelengths at around 10 and 20 microns. But even then, it's not as bright as you would expect if 90% of the starlight were being intercepted. So what this means is that there's no natural source that looks like a galaxy where 90% of the starlight's being intercepted. So that's our first upper limit. If we can find anything with more infrared radiation coming out of it than that, then that's some extreme beyond natural sort of thing. And below that, we're going to have to sort out. We'll have to say, these are the starburst galaxies, these are the dusty galaxies, these are the ones that look strange, and maybe we should investigate further. Sorry, animation there. OK, so what we were basically trying to show is that there aren't any of these, or there are these, in the WISE data set. This is an image from WISE. The blue things are stars, because at these wavelengths, stars look very blue. And the red thing in the middle is an extended little object. It looks sort of galaxy-shaped, and it's pure red. It's much brighter at red wavelengths than blue. And that's the sort of extreme thing that we could easily find with our search when we looked through the database. And in fact, this was one of the best candidates that popped out of our search. Now, it turns out this is an artifact of the spacecraft. There was a bright star at the previous pointing, and it was sort of like getting a flashbulb in your face. And you can see that flashbulb for a few seconds afterwards, and that's what this is. This is an echo of a previous pointing at a bright star. But it shows that we would be sensitive to this. And what we found is that we didn't see any of these. And perhaps that's not too surprising, but it's the first time anyone had shown that they aren't out there. So we don't have galaxies that are all infrared emission and virtually no optical light escaping. So our big paper with our results of that first search is that these sorts of galaxies that are mid-infrared bright are very rare. We looked at 100,000 galaxies. We only had 50 that looked significantly infrared brighter than we would expect. One of them was ARP-220, so that was a nice reality check. They're all probably starburst galaxies, like ARP-220. And indeed, there was a follow-up paper by Michael Garrett who looked at what's called the mid-infrared radio correlation. And he showed that our sample of 50 falls just basically like you would expect, comparing the green and the red, essentially what you expect for starburst galaxies. So they're almost all certainly starburst, which is sort of what we knew. But this is the first big upper limit. It's the first time someone has looked for waste heat. And we didn't expect to find anything right away because we're just learning how to do this. When I was explaining this, a friend pointed me to a referee comment on a famous paper by Davis in 1955, who would eventually go on to discover neutrinos. And they published a paper looking for the solar neutrinos, but their first attempts did not have the sensitivity required to detect them. And the referee was not impressed by their first paper and wrote, "Any experiment such as this, which does not have the requisite sensitivity, really has no bearing on the question of the existence of neutrinos. To illustrate my point, one would not write a scientific paper describing an experiment in which an experimenter stood on a mountain, reached for the moon, and concluded the moon was more than 8 feet from the top of the mountain." To which I reply, if you have no idea how high the moon is, that's a great first try. I mean, that only seems silly because you know the answer. So you got to start somewhere, and indeed, I'm sure that people in antiquity tried exactly that to see if they could get any closer to the moon on a mountaintop. And so this is just a first try, but we can actually do much better. Now that we know what we're doing, we can better model that dust and look at galaxies in more detail and say, yes, that's because of dust. We can get rid of that. There are all sorts of contaminating sources that we had to sift through. We have better ways to go and exclude those from the search. And we can focus on sources where our sensitivity is high. That is, we can look at galaxies that we know don't have any dust, elliptical galaxies, measure their infrared output. And there we'll be very sensitive because we know there's no dust, and so we should hardly see any infrared radiation at all. So anything we see will be interesting. So that's where we were with our waste heat search when the private philanthropic money ran out, and so that's moving very slowly now. But then another opportunity came up, which you might have heard about, and I'm going to talk about next on a completely different angle. We were talking about Type 3 civilizations before. We go back to those stars with too much heat. That's the Type 2 civilization. On your way to a Type 2 civilization, though, before you block 90% of a starlight, you block 50. And before that, you block 10. And before that, you block 1. And so, how would you notice if a star only had 1% coverage of the energy coming out of it from something that was on its way up? And the answer is that sometimes the solar panels will pass in front of the star. So this is a technique that we use to find planets orbiting other stars. Every time the planet goes in front of the star, if the alignment is just right, the star will appear to get slightly dimmer. So for scale, if it's a planet the size of Jupiter around a star the size of the Sun, the star gets about 1% dimmer, which you can actually detect with high-quality amateur equipment from the ground. And many people have done that now that we know where to look and which stars have these planets. The Kepler spacecraft was designed to detect things much smaller than planets the size of Jupiter, but planets the size of Earth. So it searched over 150,000 stars in its prime mission of 4 years to see these planets passing in front of the star. It was very sensitive to them. Before it launched, though, an astronomer named Luke Arnold published an intriguing paper in which he pointed out that, it's not just planets that you will be sensitive to. If there are huge swarms of solar panels, if you have an alien civilization doing this, if the panel passes in front of the star, you'll see that too. And he wanted to know, could you distinguish a planet from a panel if the panel didn't have a circular aspect? Because why would they build it in the shape of a circle? So not because they would do this, but just to illustrate his point, he said, could you, for instance, tell the difference between a circle and a triangle? So if an alien civilization had for whatever reason, triangular one, would Kepler notice the difference? These are both the size of Jupiter. And so if you ask what this shape is, this characteristic shape that you see where it gets dimmer and then brighter again, for a circle versus a triangle, are they any different? So he subtracted the two cases after calculating them, and it's mostly at those corners where there's a difference. But yeah, there would be a detectable difference, which means for Jupiter-sized objects, Kepler could tell this thing is not round. And planets have to be round, more or less. And so that would be interesting and suggested people look for that. He also got very creative and said, hey, if they build these things, why not build them in funny shapes that could send us information? And so he imagined more complex structures with louvers that could signal us and flash us Morse code and things and give us very complex transit signatures as well. And it's a neat idea that you might communicate information that way. You might have the solar panels fly in formation to share an orbit, which planets don't do. And then you would see perhaps patterns of them go by. And if they aligned them in certain ways that were obviously unnatural, he said that would be a good way to communicate, here we are. We have solar panels arranged in prime number sequences in the same orbit. There's no way you would mistake this for a planet, is his point. So if there's solar panels out there, Kepler should be able to find them. And I said, well, that's a neat idea. Once Kepler finished its prime mission, well, did it see any? And so we should be able to say these things aren't out there now that we have all this great Kepler data. And so I went to write a paper about this, ask all the different ways that these sorts of megastructures would be distinguished from planets, and then ask what limit can we put on each of these different things that you might see. So our team identified 10 possible anomalies that you might see around a star if it had these giant solar panels. Luke Arnold had the first one, that the shape of the transit would be different. But it turns out there's a lot of different things you might expect. He said you might have variable depths, that is, variable sizes, as different sized objects passed in front of the star. There might be many different panels, and so it might not seem periodic the way that a planet does, because you have lots of slow-moving panels in different orbits. They also don't have a lot of mass, probably, and so it's possible that they experience significant non-gravitational acceleration. That is, just the pressure of the light striking them might be enough to alter their orbits. And it turns out you can also tell that from light curves. So, and then there also might just be a swarm of them. It could be it's not just one thing going around. The star might be surrounded by a whole swarm of solar panels, some bigger than others. And when the big ones go by, you might see that. And it might be a very confusing, complex light curve that you see. And then we also suggested some ways that you could diagnose them and try and figure out what was going on. Now, all of the things I've listed, there's a natural way that you could create that sort of signal. And indeed, many of these signals are seen in the Kepler data. If a planet has rings, then it's not a circle. Its aspect is non-circular, and so you should get a strange-shaped light curve. If it has a massive moon, like the mass of Earth, that will make it wobble, which will throw off the timing, and the moon itself will block the starlight, which will give you a strange transit curve. And so we tried to think of all of the different ways that you could create these anomalies naturally, which just goes to show that there's natural scientific reasons to go looking for them as well. This isn't just a SETI search. You go looking for these sorts of anomalies in the data set, and you'll either discover aliens, cool, or you'll discover one of these other amazing things like exomoons and rings and things like that. So it's natural science as well as SETI. So we wanted to put our upper limits on all of these, but the point was that the really obvious stuff, the Luke Arnold gigantic solar panels that would, yes, that's definitely not a planet. Kepler didn't see any of those, or would have been all over the news, right? Right? Well, it turns out that there's a lot of Kepler data. And the way that they go looking for the planets often involves algorithms, because 150,000 stars, 4 years of light curves, it's just too much for people to, with their eyeballs, check every one and say, hey, that's funny. So most of the results you've heard about have come out of these automated pipelines that know what they're looking for. And if they see something really strange, they don't say, hey, what's this? They say, not a planet, and throw it out. So some regions of parameter space that turned out to have unexpected signals popped up. This is KIC 1255, 75, 48, more familiarly known as KIC 1255, obviously. And check out this light curve. So what you're seeing is the brightness of the star with time over the course of 15 days. And every day or so, it gets about 0.5% dimmer, or sometimes 1% dimmer, which is consistent with something like Jupiter going around it in an ultra-short period orbit. So it's orbiting about once a day. But you'll notice the depths aren't constant. And that's not resolution. That's real. Like, it's variable depth. And that's exactly what Luke Arnold said we should be looking for. Variable depths as different sized things in a common orbit go in front. So that's kind of neat. I feel like Luke should have gotten a citation there. It was like, wow, you thought that might happen. And we saw it. Now, not that this is aliens. Let's look a little closer at one of those dips, by the way. That's, if you stack them all up and take an average, that's the shape of the transit signature. And that doesn't look like the nice flat-bottomed symmetric signal that you expect from a Jupiter-sized planet. So whatever's going in front every day or so doesn't have a circular aspect. So bingo again, there it is. So what exactly are we looking at? Well, the best model is that what we're looking at is an evaporating planet. That is, the planet is too small to actually block any light from the star. But for some reason, it's giving off huge amounts of material. It's evaporating because it's so close to the star. And we see more of these. They all have very short periods. So there's a common story here that if a rocky planet gets too close to the star, it'll evaporate. And the material coming off will form a dust trail. And sometimes a lot of stuff is coming off, and sometimes not very much is coming off. And so the density of the tail varies very rapidly. And when it's dense, you get a deep transit. And when it's not dense, you get a shallow transit. And you always see first the head come in, and it quickly get darker. And then even after the planet's gone by, that tail is still in front of the star. So you get a soft fall off, which is what explains this shape. And there are a few other of these known now. They're called ultra-short period planets or evaporating planets. So that's neat. Those are there. We have a natural confounder, but there's cool science in it. One of the things we did is we said, well, if this had been an alien signal, it's possible there's information embedded in there. Luke Arnold's idea was that this would be a way to communicate information bit by bit. And so we asked, so is there information in there? And a grad student of mine, Kimberly Cartier, worked up a metric to try and determine how much information is in a signal like that, just in case. And we used this as a case to sort of see where it lands. So the way it works is that all the way on the left, 0, M, there's no information. And that's just a steady drumbeat. That's like a pure carrier signal. There's no information because it's exactly the same every single time. The only information you need to describe the depths is the depth, because it's always that number. All the way on the right, 1 would represent pure white noise. They're completely random transit depths. And that would mean either you're dealing with some very stochastic process that behaves totally randomly, or you're receiving highly compressed information, either one. And in between, you can see where things land. And so the B1 and B2, those are Luke Arnold's proposals for what these beacons might look like. You can see that they are not at 0. They contain a small amount of information, just 1, 2, 3, 5, 1, 2, 3, 5. And KIC 1255, all the way on the right on the upper panel, scores very high. It's an almost random signal. So it's a neat idea and a way to quantify this in both the time and the frequency domains. So if we ever do see one that we think's aliens, we can try and quantify how random it is. But the lesson here is that the computer algorithms to find these things are often throwing these out. This required a lot of special analysis to find and to find more like it. So that's where the Planet Hunters come in. You might be familiar with the Planet Hunters website. It's a citizen science project at the Zooniverse where citizen scientists can log in, get an account, and examine those 150,000 light curves that Kepler produced for all of those stars and try and find the things that the automated algorithms missed because they don't look like we were expecting them to look. So this is a real light curve of a real star. The star got brighter over the course of 30 days. That's probably an instrumental effect, by the way, not really it getting brighter. And looking to see if there's dips in there to identify by eye strange-looking things. There was one in particular, though, that really got the planet hunters confused. I mean, they often found strange things that almost always turned out to be instrumental glitches or something not all that interesting. But there was one that really got them puzzled. So here, this is the actual talk page of one of the stars. And this is one of the users. His handle is Nighthawk Black, explaining how he feels when he's trying to figure out what the heck he's looking at in this light curve. So in the upper right, you can see one of the light curves. It got dimmer and brighter, and that doesn't look anything like a planet transit. And then here's another plot that shows an even stranger looking curve that doesn't look anything like a planet going in front either. And so they contacted the scientist, the astronomer in charge of figuring out these anomalies. And it took her a while to convince herself that it wasn't instrumental, but real. But once it was determined to be real, people got very interested. So here are 4 different events. The scale is different on all 4 of these. The upper left is some of the first stuff that happened that got people confused. You can see there's these sort of 0.2 to 1% dimmings. Then around Kepler day 1206 on the upper right had this very complex shape. And the one that really gets me is in the lower left. Over the course of a week, it steadily got 15% dimmer. Now remember, a Jupiter-sized object would make it 1% dimmer. So whatever's blocking the starlight is many times larger than Jupiter. But it's this steady dimming, 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 and then suddenly it just snaps back to normal. And I don't know what that is. Then, in the final quarter of what turned out to be the final quarter of Kepler's mission, it just went crazy. It's almost random. And you can see, long events, short events, deep events, shallow events, just all kinds of activity as the star gets dimmer and dimmer by anywhere from fractions of a percent to over 22%. So the astronomer in charge of figuring this out, Dr. Tabitha Boyajian, was working on this and trying to solve it for years. And she had ruled everything out. And at one point, she showed me in my office and said, "What do you think this could be?" And I said, "I don't know, but the paper I am writing where I said Kepler didn't see any of these is wrong." I'm like, how many more of these are there? Like, how would we know? It took human eyeballs to identify these. So I told her that we really need to get this out and talk about it and get more eyeballs on it to figure out what's going on. And so even though she hadn't solved the mystery, she grudgingly published what she had so far, which was a lot. And it was actually the 10th paper by the Planet Hunters. The second author there is Nighthawk Black, the citizen scientist. And here's the abstract, trying to understand what's going on. And they needed to say something. They needed to have some proposal for what it could be. And so they concluded, they're highlighted, that the scenario most consistent with the data is the passage of a family of exocomet fragments, all of which associated with a single previous breakup event. So the idea is that each of those things you're seeing is a massive comet, much bigger than anything in the solar system, with an enormous tail, sort of like the evaporating planets, except bigger and denser. And that you don't just have one of these, you have a whole family of them, and each time one went by, you saw the star get dimmer by some enormous amount. It's very, very clever. And that's been the working hypothesis as to what it could be, but it's very contrived because we don't know such comets exist. We don't know why they would exist. And it turns out it's going to have some other difficulties as well. Anyway, they published this paper. They made a minor media splash. New Scientist picked it up around catching a cloud of comets orbiting a distant star. And that's where things were. But I still, had in the back of my mind, well, maybe it could be. This is, after all, what Luke Arnold's more or less said we should look for. It's what my paper said we should look for. So I should probably put my time where my mouth is, and we should go to the radio SETI people. So we teamed up with Andrew Simeon at the Berkeley SETI Research Center, and he and Dr. Boyajian and I submitted a proposal to the Green Bank Telescope at the National Radio Astronomical Observatories, and we asked for time to use the Breakthrough Initiative's backend to look for radio communication, because if they're harvesting lots of energy, maybe they're using it to make radio waves. So we submitted the proposal. It was all very fun. I was writing on my paper. And then Andrew was testifying before Congress about astrobiology, and while he was in Washington, he met a reporter for The Atlantic named Ross Anderson. And I knew something was brewing when I saw this tweet by Ross. Last night I had dinner with the director of Berkeley City Research Center. We had a fun talk. He wrote a neat little article on SETI. But one of the questions he asked Andrew was, so are you guys looking at anything interesting? Do you have any hot leads? And Andrew said, you know, there's this star. So Ross wrote another article, The Most Mysterious Star in the Galaxy. It's a great article. I really like this article. And right at the end, he interviewed me about it, and I really did give this quote. It looked like the kind of thing you might expect an alien civilization to build. Note the hedge, might expect. Not saying we found anything. I'm saying it's worth looking because you need somewhere to look. Well, it got a lot of attention. Here is one of the saner headlines that we got from BuzzFeed. Some places did well with it, others not so well. It was on The Late Show. Neil deGrasse Tyson and Stephen Colbert and Seth MacFarlane all discussed the alien megastructure star. For the record, Stephen Colbert is on Team Megastructure, and Neil is on Team Ordinary Explanation we haven't thought of yet. Seth just chuckled and said he read it on BuzzFeed, and that he said they think it's the Borg. So it was an interesting study in how the media deals with this topic, and I think it's one of the reasons it's hard to get government money is that it's hard to have a sane conversation about it without, BuzzFeed lighting its hair on fire and everyone saying we found aliens. And so there were some interesting meta-analyses why it's so hard for astronomers to discuss the possibility of alien life. And I think it's one reason NASA is so careful to make sure it's talking about discovery of microbial life or simple life forms, and to start small and not jump all the way to the science fiction, because then people start thinking about bumpy forehead aliens and bad acting and scripting, and it just gets all silly. And so it's hard. It's hard to do this without stuff spinning out of control. And so it's important to manage that. Anyway, that's not the end of the story. We did, by the way, we didn't get the telescope time at first, but then BuzzFeed hit and the media attention came, and everyone looked at the star and agreed, yes, this is really weird. No, you guys didn't make any mistakes. And the second round, we did get the time. So in October, we're going to go down to Green Bank and see what we can do. And then the star just got really weird. Bradley Schaefer is an astronomer at Louisiana State University, and he specializes in looking at these old photographic plates. Harvard College Observatory used photographic plates for 100 years to take pictures of the whole sky. And there's this sort of lost art that some astronomers still have, like Bradley, of actually taking, it's essentially a jeweler's loupe to these plates, and by eye measuring the magnitude of all the stars on these old plates. So he went to Cambridge into the stacks and he pulled out the plates with a star in it, and he measured the brightness of the star over the last 100 years. And the gray points on this chart along the top are what a typical star does. That's a check star of the same type from the same plate very nearby in the sky. And then the blue points are averages of plate values across the century from 1890 to 1990 and how bright the star was. And those are two lines suggesting more or less what the star's been doing. The scales and magnitudes, but the bottom line is basically 20%. The star is almost 20% brighter, or was in 1990 when they stopped doing the plates, than it was in 1890. The star seems to have dimmed by 20% over 100 years. Stars don't do that. That is not a thing stars do. And so he said this is the first thing other than the Kepler light curve that seems weird about what turned out the media grabbed onto the name Tabbys star after Dr. Tabitha Boyajian. Well, photographic plate photometry like this is difficult. It takes a real expert like Bradley to do it right. Other people look at the plates and came to different conclusions. The plates have all been digitized, so you can actually access the data online at not quite full fidelity, so it's a little harder that way. And so there were a pair of papers, first by Michael Hipke and also by Michael Lund. There were two papers by some mix of these people. And they came to the opposite conclusion. So the Lund paper said that the KIC 8462852, that is Tabbys star, which we believe is consistent with constant flux over the duration of the observations. Essentially what they're saying is that the quality of the photography is not good enough to make that kind of an assertion. And then Michael Hippel came to the same conclusion. In the case of this star, which has been claimed to dim by 0.16 magnitudes per century, we show the trend cannot be considered as significant. So this turned into a bit of a spat in public, on blogs and things, about who was right and who knew what they were doing, and whether you could really say that. And then, even weirder, and some astronomers, actually that I know, Ben Montet and Josh Simon, said, well, if this thing really is getting dimmer, shouldn't Kepler have noticed it get dimmer over its 4 years staring at it? And the answer is, that's really hard. Kepler was not designed to do this kind of long-term photometry. It was designed to see short-term variations from planets passing in front of the stars. So it only looked at a little part of the sky around every interesting star. And as the pointing moved around, starlight would fall out of that little region it was measuring and fall in, and so you get these trends in the photometry that are artificial, instrumental, and you can't tell really if a star is brighter at the end of the mission than it was before. However, it turns out every month Kepler took a calibration frame where it just downloaded the entire sky as it saw it. Did that every month, and those data should be good enough for that kind of measurement. So they very cleverly took the so-called full-frame images over the whole Kepler mission, learned how to do the photometry on them, and measured how much stars get brighter or dimmer. What they found is, as everyone knows, stars don't get brighter or dimmer over 4-year timescales. They stay the same. That's just the way stars are. And so they just plotted up all the stars that look like Tabby star, all the stars near Tabby star, and yeah, the stars don't do that. But there's this one outlier among all the stars they checked that got 3% dimmer over the whole mission, and it was Tabby star. So here's their photometry over 4 years of the mission. The points are their measurements from those once a month full frame images. And it goes from 1.01 at the beginning down to 0.97 at the end. So that's a 4% dimming of the star over that period. And then the black curve is the high frequency measurements. And so the big vertical lines, those are those dips I showed you earlier. But now we're looking at all 4 years, and so they're very narrow, and you can't really see their shape. So you can see all these little excursions down, but there's also this very long-term trend that they picked out. So the gray curve is their best guess at the true light curve for this object, combining long and short-term photometry. So Tabby star faded throughout the Kepler mission. And so this doesn't really confirm exactly what Bradley Schaefer saw, because the plate stopped in 1990, and this all happened much more recently. On the other hand, they looked and they saw the same thing, just at a different time. So I think this strongly confirms Bradley Schaefer's measurements and suggests that the star really is 20 or now 25% dimmer than it used to be. And so at this point, hypotheses like the comets are starting to look even more contrived, because why would comets over a century make the star dimmer? What's going on? So we're kind of all back at the drawing board at this point, trying to figure something out. And so we're also wondering, can megastructures do that? Is that what happens? So some people have sort of facetiously offered that perhaps this is a Dyson sphere under construction. You're seeing lots of material getting built. In just 100 years, they've blotted out 20% of the starlight. That seems kind of fast to me, but who knows, aliens, right? I think a more natural explanation, if you wanted to invoke the alien megastructure hypothesis, is to say that there's a swarm, and those panels are in orbit around the star, and some parts of the swarm are denser than other parts. And if they're out orbiting at 10 astronomical units or 20, they move slowly, and you'll slowly see denser parts of that swarm orbit into view. And that would naturally make the star get brighter and dimmer as dense parts of the swarm came around. So if I had to invoke megastructures to explain it, that seems consistent. You've got lots of panels of different shapes, different sizes, and the big ones make big dips, and the small ones make little dips, and then the whole swarm is sort of like a translucent screen that makes the whole thing dimmer. That explanation, the comets, and a lot of other explanations, all are actually having a lot of trouble. And that's because we go back to the waste heat. Anything, it doesn't have to be a computer, a solar panel, or whatever, it can just be dust. Anything that's around a star that intercepts the starlight is going to heat up. And once it heats up, it's got to give off infrared radiation. And once it gives off infrared radiation, we should be able to detect it. And we don't. This was not something that popped up when we looked at the WISE data set. It did not have a lot of infrared radiation. And in fact, Thompson et al. Came out with a paper, and they looked at millimeter radiation. And they didn't see anything. So this is spectral energy distribution like the ones I showed earlier. The gray line there, that's what we expect the star to have. And sure enough, on the left, at optical wavelengths, its brightnesses, those black dots, are right where you expect. The triangles on the right, the 4 triangles, are upper limits, non-detections. It cannot be brighter than this level because we don't see anything. And so the first one on the green line, that's at 20 microns. That's from WISE. And then the 3 on the right are millimeter wavelength observations made with the submillimeter array and SCUBA 2. And those curves represent how much you should expect if you have cold dust of certain amounts. And so they measure things in Earth masses, but for the purposes of this talk, let me translate things into fractions of starlight being absorbed. So I've translated all these measurements into slightly different units here. The black curve is what would happen if 20% of the starlight, like Bradley Schaefer measures, was being collected by a swarm of stuff, whether it's dust or solar panels or anything, and it was all coming out at 65 Kelvin, which is pretty cold. If you make it colder, that bump moves to the right a little. If you make it warmer, it moves to the left. And that is ruled out by factor of 100 by those upper limits. 20% of the starlight is not being reprocessed into the thermal infrared or to the millimeter. In fact, the purple line is if only 0.2% of the starlight's being reprocessed by anything. And that's barely consistent with the curve. So what this says is that whatever's blocking the starlight, it can't be isotropic. It's not surrounding the whole star. It must be along our line of sight. So you could do that if it's in a disk of some kind. And that hopefully will help constrain what the heck is going on. But I think it's almost a fatal blow against the idea that there's a spherical swarm of megastructures around it. Now, the way out is that, of course, the alien civilization could be doing something with the observation, with the radiation. That is, it's allowed under the laws of thermodynamics to use some fraction of the energy in a low entropy way and only dump the last bits out at high entropy. So but it can't keep it. So what do you do with energy if you can't keep it, if you don't radiate it away? Well, I guess you could turn it into mass. That's a low entropy way to do things, but that seems hard. It could radiate it away at low entropy as communication. They could use it, as Kardashev originally proposed, as radio. So if that's right, then maybe there's something to hear with the radio waves. So the Allen Telescope Array has already pointed at it and done a pretty deep stare. And they had a nice, the SETI Institute had a nice paper about their non-detection of radio. So when they looked at the frequencies, they looked at the sensitivity they had, they did not see, there was no strong radio transmission coming out. I should also mention, if they were to do that at 20%, the maximum efficiency they can have is 99%, which means this is just barely at the edge of possibility according to thermodynamics. If they're collecting 20% of the starlight, then of that 20%, they're allowed to beam out 99% of it, but the other 1% has to come out in the infrared. And that's the purple line, which is just barely consistent with what we have. Anyway, so if that's what's going on, and it's an even longer shot today than it was when we first proposed it, I think, then hopefully we'll be able to see something with the Green Bank telescope when we head out in October and get a nice big data set on it. And while we're there, I'm trying to see if we can also maybe look for stuff along the line of sight that might be able to explain what's going on. So I'd say we have no good explanations right now for what's going on with Tabbys star. We've been sort of crossing off of our list of bad explanations more and more things as we get more data. We still have a couple ideas. I'm working on a paper right now about what really could be going on. But for now, it's still a mystery. And I think one of the things that Tabbys star teaches us is about the value of this non-communication SETI and what it offers. Essentially, artifact SETI, we see something and we're really hard pressed to say it's not natural. Without some kind of like prime numbers or something like that, there's no reason to say it's just dust or you just haven't thought of the right thing yet. Communication SETI looks for obviously intelligent signals, but has to cast this impossibly wide net. You don't know where to look, you don't know when to look, you don't know what frequencies to use. It's this huge sea of possibility, and you're kind of going through, as Joel Tarter likes to say, one glass at a time, looking through this whole ocean. So, but that means these are complementary approaches. The artifact SETI approach can find the anomalies and then hand them off to the communication SETI folks to enrich their target list and give them better targets to look at than sort of pointing blindly. So at least we know where to look. And so I think together the two forms of SETI are pretty powerful, and I'm glad to have contributed in that way. And that's the story of Tabbys.